full response. There is another one.
There's another one.
Oh, so it's one.
Don't you just have to change the microphone input? Okay, that's good again.
Hello? Hello? Okay.
Okay.
Okay. Is Maxim on?
He said he was coming, so
I guess sometimes we should use this to be here. Yeah. Okay.
can you hear me on this?
Let's start.
If the audience on Zoom can't hear me, hopefully they can send a message and
Sure.
we can work things out.
Yeah.
Are we starting?
Can you please spell your last name?
My last name,
Madden?
Madden.
Madden. All right, let's start our seminar. Today we're happy to have Amalia Madden, who is a student at the Institute, and she'll tell us about piezoaxionic effect.
Thank you, and thank you very much for having me here. So today I'm going to tell you about a new observable, a new experimental observable that we hope could be used to look for the QCD axion. So an outline about what I'm going to talk about. I'll start by motivating the QCD axion. I'll talk about two new observables today that require a kind of material known as a piezoelectric material. The first effect, which we've already published, is known as the piezoaxionic effect. And in order to understand this, I'll have to tell you a bit about parity and time violation in nuclei, in atoms, and in crystals. I'll tell you about a proposed experimental setup to look for the piezoaxionic effect. And then at the end, I'll tell you about something you were working on, which is a second effect using piezoelectric crystals, where we're actually going to source axion-mediated forces. And we've called this the ferroaxionic effect. So one of our main pieces of motivation here is dark matter. So I'm sure you all know a lot about. So you want to ask yourself, what is this dark matter made out of? What problems does it solve in the standard model? How do you produce the dark matter, and how do we detect the dark matter? And the dark matter candidate that's going to interest us today is the QCD axion. And I want to show you a cute classical picture of how the strong CP problem works. And I learned about this from Anson Hook at Maryland. So the analogy is going to start with a water molecule. And we know the angle between the hydrogen and the oxygen ions in a water molecule. We roughly know the bond distance. It's about an angstrom, so 10 to the minus 10 meters. And then we can ask ourselves, how big do we think the electric dipole moment of water is? And just by naive dimensional analysis, these numbers at the top here give you something very close to the measured value, which is about 3 times 10 to the minus 11 times the charge of electron times a meter. And if you look at this, you would ask yourself, well, how do we understand this angle and this distance? Is this random? And probably think, no, it's not random. The way we understand it is that inside our oxygen molecule, 2 of our electrons from the oxygen ion form bonding pairs with hydrogen. You have 4 left. They repel each other in these negative density areas here. And the result is that the equilibrium configuration for this molecule is a tetrahedral structure. So now we can ask ourselves the same thing for a neutron. What do we think the electric dipole moment is going to be for a neutron? And we know the size of a neutron is roughly 10 to the minus 15 meters. It turns out when we do the standard model calculation that actually the electric dipole moment you expect as a function of this angle between the up and down quarks is slightly smaller than your naive dimensional analysis. However, when we try to measure this, we find that our answer is still way off. We have an upper bound, and it's about 10 to the minus 26 times the charge of electron times a centimeter, which means that our theta angle, which we might have expected to be order 1, is actually smaller than 1 part in 10 to the 10. Really, really small. So again, we look at this and we say, how can we explain this? Is there a dynamical explanation? And you may know one of the proposed solutions to this problem is the QCD axion, probably the most well-motivated solution. And to just summarize how the solution works, your effective theta angle is not just your theta naught, which couples to your gluons, but also depends on the mass matrices of the quarks. Now we introduce the axion field, which is coupled to QCD. And I have to apologize, I realized that when I took these slides, I missed one line, which is that theta naught here should couple like this, so I apologize. Couples like the axion. And the way the axion solution works is that QCD generates a potential for the axion. And when the axion relaxes to the minimum of this QCD generated potential, you can dynamically solve the strong CP problem. And now your effective angle is at 0. So the next piece of information that we need to understand about QCD axion in the context of dark matter is that when the axion, which is a boson, becomes very, very light, it becomes more convenient to think of the axion as a wave than our traditional picture of particles. This transition happens when the number density of axions is bigger than about 1 over the de Broglie wavelength cubed, and that in our galaxy is about 1 electron volt. And in this picture, we now have that our axion forms a classical wave with its frequency set by its mass. Its amplitude is determined by the square root of the dark matter density and is inversely proportional to the axion mass. And there's a small spread in its frequency that's set by the kinetic energy, the spread in kinetic energy of the axion in the galaxy. And that's about 1 part in 10 to the 6. Now, if you remember from the beginning, one of the other things that tell us that our dark matter model is really well motivated is if we have a consistent production mechanism. And what will be relevant here is the misalignment mechanism. So for those that don't know about this, the idea is that in the early universe, or in the universe, the axion has an equation of motion, where here these dots refer to its time derivative, where the friction is set by the Hubble parameter. Now, early in the universe, when it's very hot, the mass of the axion is below the Hubble scale, and the axion is frozen by friction at the top of its potential. Whereas the universe cools, the Hubble scale will fall below the mass of the axion, and it will begin to oscillate around its minimum. And these coherent oscillations of the axion around its minimum redshift like dark matter, and its energy density today is determined by its initial angle, where it was initially frozen in the universe, and the axion decay constant. So where should we look for the QCD axion? So there are many orders of magnitude where the QCD axion could live. At the very top here, we're constrained in that here we're constrained by stellar cooling. So the existence of the axion starts to cool too fast. At the very bottom, we have a bound from the fact that you would affect the dynamics of our smallest dwarf galaxies when the wavelength of the axion becomes comparable to the size of these galaxies. Now, in between, we have this huge range that we could look for the axion. At around 10 to the minus 11 electron volts, we're already constrained by superradiance of black holes. And our only sizable lab-based constraint at the moment on the QCD axion comes from the ADMX experiment. So this is a microwave cavity experiment that looks for the axion coupling to photons. And that's constrained a small region above around 10 to the minus 6 electron volts, and should in the near future look for the axion in this range up to 10 to the minus 5 electron volts. So where does the piezoaxionic effect fit into this picture? Yes?
Can we actually go below 10 to the minus 12 eV? The decay constant will be larger than the Planck scale.
Yeah, so you might say that, yeah, you're right. It's perhaps less well motivated, but I wanted to give you the whole picture here. Yeah. No, I agree with you. So yeah, our effect is above, has an FA above the Planck scale. So the piezoaxionic effect could fit in here. I'm going to tell you what it is in the next slide. And this experiment could probe around 10 to the minus 11 to 10 to the minus 7 electron volts. And then at the end, I'm going to tell you about the second experimental proposal using piezoelectric crystals that can probe a range between 10 to the minus 5 to 10 to the minus 2 electron volts.
You're also assuming that there's dark matter production. You don't care about how cheap it's
No. Yeah. I can see there's some questions on the chat. I don't know if anybody else is looking at those. I'm not sure I can open them. Can you see them? Okay,
Yes.
everything's okay.
So, 2 slides ago, you said in our galaxy, MDM is smaller than 1 eV.
Mhm.
That
That just comes, can I go back? Sorry, it's frozen. So it comes from this condition here. So you look at the number density of the dark matter in the universe, and you look at 1 over the de Broglie wavelength cube of our dark matter in the universe. If you plug in the parameters for our universe, you find that's about 1 electron volt.
okay, you just want the dark matter to be wavelength.
Yes.
And the scale of our galaxy.
Mhm.
itself.
Yeah.
That's an ad hoc assumption.
Yeah, so I mean, this is just convenience. It's not that some crazy phase transition happens at 1 electron volt, just that around that time, this becomes a better picture. Okay, now I can tell you about the real idea. So here is a picture of our idea. So we're going to take a piezoelectric crystal. We're going to apply an external magnetic field because inside this crystal, we're going to have, its composition is going to have nuclei that have spins. So this external magnetic field is going to polarize all of the nuclear spins in our piezoelectric crystal in the same direction. Now, if the axion is the dark matter and we're living in some background of light, wavy axion dark matter, through the axions coupling to gluons, it's going to induce the following effect. Our crystal is going to oscillate. So it's going to deform in size, and the frequency of these oscillations are going to be set by the mass of the dark matter, so the mass of the axion. So what's a piezoelectric crystal? So you may have heard about these before because they're used in things like microphones, guitar pickups, sensors. And what's going on in a piezoelectric crystal is it has a structure where the position of the ions in its lattice intrinsically break parity. So you can see it in this picture here. The result is that if you, for example, in this quartz crystal here, if you were to deform it in one direction, you'd have a net positive charge on one side of the unit cell, net negative charge on the other. Whereas here at compression, you switch around the net charge on this unit cell. And in practical applications, what that means is that you have a crystal where if you squish it, you can produce a net charge.
Sorry, where does the net charge come from?
Okay, so if you look at this picture,
Yeah.
this unit cell just is neutral. However, it has a very strange arrangement of the ions here. And because the arrangement of this ions is parity violating, then what happens is that when you deform it, because it's parity violating, when you deform it, the ions will then align themselves in the crystal such that in the unit cell, you now have, in this case, because of these positive charges here, you have more positive on this side. And because of these negative charges here, you have more negative on that side. Okay. Okay, sorry, I apologize. I have explained that poorly. What I mean to say is a dipole moment. Yes, I'm sorry. Yeah.
Changes when you come.
Yeah.
First, so if it becomes a crystal, then you have those kind of structures repeated, right?
Yes.
Then the net effect is coming from surface of the crystal, or
yeah, I guess. I mean, it's like having some density of polarization inside your crystal. So like a polarization field that you could have in a dielectric.
but I think like each like atom feels like the local dipole, right? Like you're asking, do they just like cancel out? Yeah, exactly. But I think the point is that each atom just feels just locally happening around it. Right. So they don't really.
So how can we understand this in terms of equations? In terms of symmetries, so our mechanical variables here, stress and strain, these are parity even, whereas our electrical variables here, the electric field and the electric displacement are parity odd. The special property of a piezoelectric crystal is that this piezoelectric coefficient is also parity odd. And what that means is that if you apply some electric displacement, you can get a mechanical stress out. What changes when we have an axion? So our axion field is both, here our theta angle is both parity odd and time reversal odd. So in order to produce mechanical stress, for example, directly from this axion field, we need a coefficient that's parity odd, but we need one more thing, and that is we need to polarize our nuclear spins to introduce some time reversal oddness. And as you can see, this piezoaxionic coefficient has the same symmetry properties as the piezoelectric coefficient. So this is only present in piezoelectric crystals. Now I should add there is another effect. So you can directly produce an electric field from the theta angle if you have a nuclear spin as well, through this electroaxionic coefficient, which has the same symmetry properties as the permittivity. So this effect will be present, but I'm going to focus today on the piezoaxionic effect because, as you'll see at the end, it's the larger effect.
Please forgive my ignorance, I'm from Cognos network community.
Of course, yeah.
Sorry, that heard. In this like low energy sector, we can view all this axionic stuff as an additional contribution to the Lagrangian,
Yes.
which is determined by the product of the electrical field and the magnetic field, like U, E, B term, right? No?
Amalia is going to use not B because this is a derivative, so it will always be proportional. I mean, like it's total derivative, so you'll be always proportional to the derivative of the axion field. From my understanding, she's going to use some nuclear EM by theta. So it will be an electric dipole of a nucleus aligned with the spin.
And you have the contribution of the like for external magnetic field to this electrical field.
There are different couplings for the axion. I think the one you're thinking of is the axion photon coupling.
Yes, that's what I was wondering. So a lot of experiments that look for the axion probe a model dependent coupling of the axion to photon. Actually, what's really interesting about this, and I should have emphasized it already, is that the axion coupling to gluons is model independent.
Okay.
Okay, should I continue?
Sure.
Okay. So just to emphasize again, the piezoaxionic tensor is odd under parity and can only be present in piezoelectric materials. The electroaxionic tensor is even under parity and could be present in all dielectrics, but as we will see, it's better to focus on the piezoaxionic tensor. I can give you a sneak preview why. Essentially, the piezoaxionic tensor we're going to find can be enhanced resonantly. How big is the piezoaxionic effect? To understand this, we have to think about how it's induced. And as you saw at the beginning of this presentation, we know that the QCD axion can induce a dipole moment of the nucleus. And moreover, because we're looking at these low mass wavy-like axions, we're going to think about an oscillating nuclear electric dipole moment. So here's our picture of what's going on. And then we hope that the potential from this nuclear electric dipole moment will induce a potential on the electrons in your crystal that will also cause them to oscillate, or rather will cause an oscillating mechanical stress in this crystal. This picture is too simple. I'm going to tell you why it doesn't work. So there's something known as Schiff's theorem. So if you were to treat an atom as a system of static and point-like particles, then the electric dipole moment of your nucleus would be perfectly shielded by the cloud of electrons. So to give you a picture of how this works, you see we gave the nucleus a dipole moment, and it's shifted its position relative to the cloud of electrons such that it exactly cancels out the net dipole moment of the system. So how do we get around that? And the way we get around that, it can vary depending on your system. The way we get around this is finite size effects. So now what happens is that the potential that your electrons feel from the dipole moment of the nucleus is no longer caused by the dipole moment of the nucleus, but actually a higher order effect known as the shift moment. And this here is going to act on the electron wave function. So there's two different ways that we can see how the shift moment scales, and that depends on the shape of our nucleus. So if you have a spherical nucleus, the scaling looks like this. So here's how the axion enters, and it depends on the area of the nucleus. And this will scale like the number of nucleons to the power of 2/3. However, there's these kind of special nuclei that are intrinsically octapole deformed, so they have a pear shape. And in that, quite complicated to explain how this happens, but actually you get an additional Z enhancement at the level of this operator here. And so these will be more relevant for us. And for those who are more familiar with this topic, I want to tell you about how this shift moment comes about. Actually, what happens is it's not, for example, the axion directly inducing a dipole moment of a neutron that generates a shift moment, but actually inside your nucleus, you have these parity and time violating forces that are mediated by pions that cause the internal nucleon potential that generates these shift moments. So that was just an additional point for people who are more familiar with this. Is everybody following, by the way? Feel free to ask me if you have some questions.
What was this vertex on the right?
Oops, sorry, I need to go back. Okay, so this, oh God.
More or less.
Okay, I'll do this more slowly. Okay. So this here, the way people understand this is they look at chiral perturbation theory, and they see that the axion can induce a vertex between pions and nucleons that's parity and time violating.
In one vertex, it's important point here that two vertices different. In one vertex, the pion is proposed to a mass of 1 neutron or less, something like that. And another vertex is according to a gradient of the pion field is dotted with the spin of the neutron. Yeah, that's a normal vertex pion. And when it couples per mass, it's different.
So now we understand what this parity and time violating, sorry, this parity violating potential of a nucleus looks like. How do we understand how it affects the electrons in our crystal? And in this case of a dielectric, we can think of the electron wave function as similar to a hydrogen wave function. So we have hydrogen-like s and p orbitals, and as you might know, s and p orbitals are opposite parity states. And what happens in a piezoelectric crystal, because your piezoelectric crystal intrinsically violates parity, your ground state electron wave function is no longer either pure s-like or pure p-like, but contains an admixture of these two opposite parity orbitals. And we've denoted this fraction of s and this fraction of p by these epsilons. Now, if you have a shift potential from your nucleus, the naive dimensional analysis would tell you that your piezoaxionic tensor is going to depend on the size of your shift moment, the size of your unit cell, And this very interesting factor here, which is how this admixture of S and P changes as you strain the unit cell.
Just to make sure, in this crystal, the ratio of so when the epsilon S and epsilon P have to have different properties on the complex conjugate, right? So usually, if you have the time reversal is preserved, then a mixture of S and P occurs via an imaginary I, right?
I think so. I need to think about that more carefully, Maxime.
Usually, if this is both real, that is also means the time.
Yeah, I mean, this should, sorry, I should have written a complex conjugate. Here, you're right. When I did the calculation, indeed, you need to have some properties under complex conjugate.
Yeah, nice. Yeah.
So this factor here, we think from naive dimensional analysis that it should be of order 1. But I should be clear, this is something that we need to understand better. And we had an attempt at understanding this ourselves using something called density functional theory. And it was beyond our capabilities as particle physicists to actually calculate this. So we're hoping it's something that we can improve on in the future. However, one thing we do know, and I'll mention this, is that we think that this should be related to how strongly piezoelectric the crystal is. So a crystal that has strong piezoelectric properties, we think would also have a larger factor here. So what can we compare this to understand how big this effect is? And one thing we can think about is the equivalent strain that would be produced in this crystal by the piezoaxionic effect, sorry. So a strain is just your dimensionless changing length of your crystal. And as we said, it's related to this piezoaxionic tensor that depends on your shift potential and how strongly piezoelectric your crystal is.
Sorry, the shift moment is concentrated on basically on the location of the every.
Yes.
And
no,
you
you're
need to figure out how this external wave functions of electrons feel that.
Yeah, no, you're absolutely right. So when we try to understand this, the first thing we try to do is see how our piezoelectric is to understand this in terms of piezoelectric tensor. But then, of course, the caveat that you've just pointed out is that this shift that what's relevant here is your electron wave function at the point of your heavy nucleus. And so that's why you can't directly compare the two. And that's why we have difficulty calculating this. So you're absolutely right. It depends on the stiffness of your crystal. It depends on your nuclear spin polarization, and it depends on your theta angle.
But at a certain level, this is an atomic/molecular question, right? So the any wave function becomes pretty much universal behavior when it comes to very near this heavy nucleus. So it's more of a question of matching of that behavior with realistic wave functions.
Yeah. We have not understood how to do it yet. Maybe you have some ideas. Okay, so we think this strain is of the order of 10 to the minus 26, which sounds really tiny. I'm going to tell you why this might be very interesting. So another direction here that we're going to talk about is, well, not another direction, something completely different that I'm going to introduce you to is resonant mass detectors. So the first resonant mass detector I'll tell you about is the Weber bar. So in the 1960s, Weber wanted to find gravitational waves. So he took these huge kind of meter-sized chunks of aluminium, and the idea was that the gravitational wave would pass through and he would detect a strain. And then he could read out these strains. Actually, he used transducers that were piezoelectric crystals. And he could not reach gravitational waves because he could only reach strains of 10 to the minus 17. Fast forward, there are now modern incarnations of these resonant mass detectors. So examples are experiments that go under the names of Auriga and Nautilus. And they're detecting strains at about 10 to the minus 25. But to be clear, this is now a sensitivity to scalar dark matter that I quoted here, not gravitational waves. Another interesting resonant mass detection experiment is this here that was built in Australia. This is a quartz crystal, so it's already a piezoelectric crystal, and it's looking for strains at about 10 to the minus 22 in a frequency band that's possibly more similar to what we're thinking about. And so these things are not far off. So what's our proposed experimental setup? So find a piezoelectric material that has very low mechanical noise, otherwise known as having a very high quality factor. And it contains some nuclei that have really big shift moments. We want to align the nuclear spins then in this material using an external magnetic field. But just to be clear, because this point has come up a lot, once you've aligned the spins, you can actually greatly reduce the strength of your magnetic field. So we don't have to worry about, to the same extent as some other proposals about magnetic noise in our experiment. We want to cool our experiment to around 1 millikelvin. So this is really on the threshold of what people can do at the moment. And the reason being that we want to reduce thermal noise. And also by cooling to 1 millikelvin, we can achieve higher nuclear spin polarization. And then we want to measure this possibility of a tiny oscillating voltage in our crystal using a squid. So if you remember, this is a piezoelectric crystal. So if we can induce some mechanical strain in our crystal, the crystal will automatically turn that into an oscillating voltage for us.
Sorry, you cool it first or you align it first?
That's a very good point. We have to cool it first and then align it. Thank you. No, you're absolutely right. Okay. So what kind of material would be good for this proposal? So we want a material that has a high density of nuclei with big shift moments and low radioactivity, good acoustic properties, so we want low thermal noise, possibly strong piezoelectric properties. As we said, this might have a connection to this order 1 factor we mentioned. And then since we're probably dealing with a material that nobody's used in this context before, it's helpful if it has some structural similarity to a crystal that's already used in resonators, just so that we know how to deal with it, how to grow it, how to cut it in the right way.
Sorry, I want to understand in the end how you're going to scan. Is this
I'm getting to the scanning, Maxime.
Separately?
It's on the slide just after this one. Can you wait? Okay. So since we're not using a crystal that people have really manufactured before, we went on this website called the Materials Project, and we looked for crystals that people had already grown. And we tried to look at their symmetry group, and if people had used them in a similar context, like a resonator, but we tried to find now similar materials that had nuclei with big shift moments. So 2 useful nuclei for this could be dysprosium, which is octapole deformed, and uranium-235, which is octapole deformed, but it has a very, very long half-life. So it's not strongly radioactive. It might still be contentious to get uranium, but we've put it there anyway. Okay, scanning. So you may have realized, since we want to detect the axion resonantly, the ideal situation is when the axion's frequency just happens to match the natural frequency of your crystal. In practice, you would need to grow a very large number of crystals in order to achieve that. So scanning is going to be a problem for us, but one way around this is that we can widen the bandwidth of our experiment by introducing, as Maxime suggested, an external LC circuit. And that external LC circuit can't change the mechanical resonant frequency of your crystal, but it can change the electrical response of your experiment. And that allows you to scan very slightly outside this like predetermined natural frequency of your crystal.
Does this like degrade the hue of your lens?
So that we don't think so. So we've looked, for example, at the projections from something like dark matter radio, where their external LC circuit has very high quality factors. So we think it should be fine. We've included the losses in this external capacitor and inductor in our final sensitivity plot. So we have incorporated that, yes.
But in practice, how wide the scan can be around this mechanical frequency?
It's not great. I don't have a number for you, but I can show you the figure at the end, and then you can see it. You can see it visually. So no, scanning is an issue.
Can I go back one slide?
Mm-hmm. Yep.
About the requirements. You know, what's the relationship between those different requirements? The large shift moments neither have a necessary condition to have a strong piezoelectric property. Have you require them separately?
I require them separately. So you can have a very strong having a strongly piezoelectric crystal has nothing to do with having these large shift moments. And in fact, I mean, the ideal situation would be if we could find something with all of these things, because this would make our effect as big as possible. In practice, we might not be able to max out all of these, but this would be ideal.
Sure, but can you just remind me again,
Mm-hmm.
why do we require large shift moments?
Okay.
To have axial response?
Okay, so I'm going to go back.
I didn't mean to.
No, it's fine. No, I'm glad. I really want to make sure you understand, so it's fine. So if you remember, the potential of the dipole potential of a nucleus is screened because of Schiff's theorem. And the way we get around this is by looking at this higher order moment, which is the shift moment. And in order to make the potential of the electrons field from the nucleus as large as possible, you want to max out the shift moment. And this shift moment is is bigger in heavy nuclei, for instance, or in octapole-deformed nuclei. And if you remember, the way the axion enters here is that it enters from the fact that this shift moment of the nucleus is generated by these internuclear forces that are mediated by pions and have a vertex that depends on the axion. Is that clear now? Okay. So what would the backgrounds for this experiment be? So you could have fluctuating nuclear spins and fluctuating magnetic impurities. These are both small. So for instance, we're not probing the NMR frequency of our crystal. So whereas this has been a problem in other proposals, it's not for us. And for magnetic purities, in order for this to be negligible for us, we need less than 1 part per million of magnetic impurities in these crystals. We've seen that people have grown similar crystals with impurities of less than 1 part per billion. So we think this is achievable. Vibrational noise has already been demonstrated at this experiment that I showed you called Auriga, which leaves us with our main noise sources being thermal noise from the crystal, which we try to reduce by cooling it down, and also growing crystals with very high quality factors. Also, for example, we restrict ourselves to pure crystals and crystals that aren't, for example, ferroelectric, so there would be no domain structure. And our other main source is so we use a readout, which is a squid, and there's some intrinsic noise in our squid that would limit us. So here's our ideal forecast. So we're looking, for those at the back that might struggle to see this is the axion mass along this axis. So we're looking at a range from around 10 to the minus 11 to 10 to the minus 7 electron volts, which is frequencies from around 10 to the 4 to 10 to the 8 hertz. And this yellow region here is all of the parameter space that we think this experiment could potentially reach. And just to be clear, we're very interested in reaching the QCD axion line, because when you're looking at the axion coupling to gluons, this parameter space above the QCD axion line is more finely tuned and less well motivated. So here, this line here is for the piezoaxionic effect. If you remember right back to the beginning, I told you there's also an electroaxionic effect that would be present in all dielectrics. And that line is actually up here, which is why I focused on the piezoaxionic effect. And just for completeness, these two shaded regions depend on the noise of your squid. So if your squid is at the squid noise is at the quantum limit, you would have this lower line here, which we would hope to achieve. The kind of squid you can get off the shelf at the moment, its noise temperature is a factor of 20 higher.
I'm confused. Why dwarf and sun lines are at an angle? Aren't they just sensitive to the coupling, not to the mass? You have a mass on the x-axis and the coupling on y.
Yeah, I need to.
Mass has nothing to do with it. I suspect these lines are wrong.
I think it's come from a different source. It's not by producing axions.
Oh no, this isn't to do with cooling, for example, Maxime. So these are things here to do with the effect of the axion potential changing in media that have very high density. So for example, this line here comes from the fact that you would change the mass to radius relationship of a white dwarf because there's very high densities in there.
It's below the.
Yeah, so they're way up there. Yeah, they're not here. Is that clear now? No, don't need to apologize.
It's just anywhere above this green line, the model is technical and natural. But
I know.
Because if you went down to the QCD line, there's the parameters just follow the QCD line.
Yeah, and I'm going to tell you what those parameters are now. The reason we stop here, for example, well, for one thing, you're getting to FAs close to the Planck scale, but the other reason is that when we're going to talk about this line here would be a crystal that's 40 centimeters big, a single crystal. So we think that pushing any further than that is unrealistic to grow. So here are two example setups. This blue one here, actually this is also 40 centimeters. And here we would actually grow 13 crystals. And they would be like a thin cube with an aspect ratio of a factor of 10. And the length of this crystal would range from 4 to 2 centimeters, 13 of them logarithmically spaced in a logarithmically spaced interval. And then we would integrate, I think the total integration time across all these crystals, and you could probably run them in parallel, would be of order of 10 years. And what you see here is these are the resonant peaks. When you hit, when the frequency of the axion matches the resonant frequency of these crystals. And then in between, we scan a bit by adjusting the external capacitor and inductor. Now here would be a higher frequency setup. So now these crystals are smaller, but we keep the total volume of our sample fixed. So it's still 40 by 40. And instead we have 128 crystals now sitting in that volume.
So each spike is a different crystal.
Yeah, I think if you count, there should be 13 spikes there. It's possible. I mean, this would also, in our calculation, you would probably also see higher resonances as well. But yeah, the crystals should correspond to the peaks of each of those 13 crystals.
Wait, the electrical scanning is not coming from changing the circuit element?
So no, it is. So the scanning is coming both from building, the way we scan comes both from building a series of crystals, like a xylophone of slightly increasingly smaller crystals. And then in between these peaks, what we do is we change the electrical properties of the circuit. So both things are going on at once.
Oh, like you'll do a run at one frequency and then you'll change the circuit to do a run at a different frequency. And those will give you.
Yeah, so you will, over your total integration time, you'll be gradually adjusting the external capacitor and inductor for each of these crystals, yes.
So I think you're saying that each spike, you get the width of the spike from changing the circuit. Moving from spike to spike, you need to change the crystal.
Yeah. So I mean, there's different ways you can potentially do the setup. It might involve you could possibly find ways to connect crystals of multiple sizes, or maybe you would connect them one at a time. We don't know the optimal way of doing this yet.
And why is that?
This is just an example. So there's nothing special about this one or this one. We just chose them for examples. Yes.
Also, you have one point that's 40 by 40 by 4 and one that's 4 by 40 by 40.
Yeah, we just changed. Okay, no, so you're right. So what we could do there is we could probe different modes of the crystal. So depending on whether you want to probe the electric field, like in the length direction or the height direction, or
Right, and it has like different resonant frequencies.
yeah, it would have different resonant frequencies, and also actually when you grow these crystals, you discover that they have different quality factors, so different amounts of mechanical loss depending on which direction you decide to probe them in. And so as you change your frequency band, different modes become more relevant.
And what is the cost of the 40 by 40 by 4? Roughly?
What's the cost? It depends on what material you use. So I don't know what the cost is going to be.
Okay, just to make sure, this is an idealized. Like,
This is idealized, yes.
Table you look up on properties and you just.
Yes. But I mean, we're not looking, yeah, it might be expensive, but we're not looking for super, I guess it is quite rare. Yeah, I don't know.
People following up and you're collaborating and presenting experimentalists?
We are collaborating with experimentalists. We're collaborating at the moment with Andy Geraci at Northwestern. So he is building the Ariadne experiment. And the thing I'm going to tell you about in the last few minutes, if I get there, he's having more of an input on that. I have been speaking to people, it's nothing serious, no paper out, no paper coming yet about, so people that can grow these crystals who are interested in researching for us. But yeah, it's an open question at the moment, what would be the ideal material, but we think it exists. We hope it exists. Something you could do more immediately is to look for the axion-electron coupling. So if you look at the non-relativistic Hamiltonian, I'll try to speak a bit more quickly now, for the axion coupling to electrons, you find that this part of your Hamiltonian is p odd and t even. And what's really interesting about that is I told you previously we needed some t oddness from polarizing nuclear spins. Now this interaction is already t even and we don't need to polarize the nuclear spins. And we're also not interested in the shift moment or the nuclear properties. So this is an experiment that you could potentially do straight away with something like quartz. Sorry, was that a hand or just a stretch? It was just a stretch, okay. Yeah, and we think you could go below current constraints from white dwarf cooling. So for the piezoaxionic effect, future directions would be precise shift moment calculations for some stable octopole deformed nuclei. We have somebody doing that for us as well at the moment. Density functional theory calculations, or maybe somebody knows another way of doing this for the piezoaxionic and electroaxionic tensors, and experimental investigation of suitable materials. Okay, we have a bit of time, so I'm going to tell you about the ferroaxionic effect. I'll tell you about some history. So in the 1880s, the Curie brothers discovered the direct piezoelectric effect. So this was a stress going to a charge. It took a whole year for people to realize that the piezoelectric effect went the other way. And you could make a charge from a stress, which the Curie brothers experimentally verified. And we had the same realization with our experiment. A year later, we realized that we could go the other way. And we're calling this the ferroaxionic effect, and I'll tell you what it is. So previously, I told you that if you had a background of axion dark matter, you could induce by the axion coupling to gluons an oscillating strain in your crystal. Now, this time, we don't need a background of axion dark matter because our crystal is going to source the axion. So we're going to have an axion-mediated force. And what that will do is through a different coupling now, which is this model-dependent axion coupling to nucleons, we can make a sample of spins process. So for those who are familiar, this is a similar concept to the Ariadne experiment.
Is there a reason why you don't just try to do the gluon coupling on both sides?
It's too small.
Oh, okay.
Yeah. Yeah. So, I mean, for a start, okay, there's two things. So this coupling here, actually, too small is not the right answer. This coupling here is actually a monopole effect at the moment on this side, and here to make the spins process as a dipole is a dipole type coupling. So here, this, yeah. So one thing is that it's a monopole coupling to a dipole coupling here, and also that the coupling induced by the gluons to the QCD axion that would be dipole-like is to, no, I mean, this is also produced by the QCD axion. I'm making things very confusing here.
But couldn't you just detect it in the same way you like detect it with a piezoaxion?
Yeah, no, we estimated that, and it, yeah, detecting it with the piezoelectric crystal ends up being too small. Yeah.
Sorry, can I say more about sourcing the action? What did you need to do to this piezoelectric?
Okay, so what do we have to do? So the reason we call it the ferroaxionic effect is because actually you now need a subclass of piezoelectric materials, which are the ferroelectric materials, because they have an extra polarization vector intrinsic to them that gives you some parity direction for your parity violation. And apart from that, you to source the axions, you don't really need to do anything. If you have a well, you need to polarize this, you need to polarize the nuclear spins, but other than that, there's nothing extra that you need to do. To build an experimental setup, there's more that we need to do that I'm going to tell you on the next slide.
Conceptually say, oh, I may find a ferro electric.
Conceptually, all you need is a ferroelectric material. You need to polarize the nuclear spins.
In one shot, I like polarize it and I release my external force, external field, whatever. They work slowly emitting axions.
Yeah.
Okay. And until it reach another state, what is the other state? It's not an equilibrium state.
Yeah, I don't know what the endpoint of this would be.
Yeah, it cannot be a permanent
Yeah.
source, right?
So is the point that the ferroelectric has some electric field in it, and
The point is that if you try to look at the symmetries of what you need to produce the axions, you find that you need some fundamental direction for your parity violation, some vector intrinsic to your crystal for your parity violation now that you didn't need previously. And that comes from the fact that a ferroelectric crystal has this parity direction set by the polarization inside the crystal. So that's quite a technical explanation.
Phrase it, requirements on the gradients of the electric fields on the location of the crystal components. So you go still using the shift moment, and so it is like a normal situation where everything is symmetric. There is no direction to any of the gradients of the electric field, right? So you have average to your part, as Amalia was saying, that there is some built-in external direction. Like if you can imagine a diatomic molecules with different types of atoms, and it's all kind of stacked up, and you polarize the spins of the heavy nuclei, it will be this. So that in the end, there will be a coupling of mass to a mass.
Also, the confused by James' question actually. So, your axion, this field, does it have any time dependence? It doesn't have.
No, we don't require, for example, the time dependence isn't necessary for this experiment. It's not like before when we have oscillating mechanical modes.
They do a time dependence for convenience. They do this perforated
Oh yeah, I'm going to tell you.
You can do that, but I mean, in principle, this coupling, you just go out
that gives a 50 force between these.
so you're not sourcing like on shell.
No, they're off shell. Yes, they're off shell.
So in a sense, that was already the point of it, right? Not to James' question.
Okay, yeah, I was a bit confused by that question, so sorry, but yeah, I'll need to think about it afterwards.
Hydrostatic potential.
Yeah, static potential. Yeah. And of course, you can just shape your.
So, as we said, off-shell axion being sourced by this scalar coupling of the axion to the piezoelectric crystal and being detected with this pseudoscalar coupling of the axion to the spins in the nucleus generates this monopole dipole potential. And what's interesting about this is that it looks like an effective magnetic field. Of course, it's not a real magnetic field. So what we can do is we can screen all the real magnetic fields in our experiment, and this will still pass through. So an example.
Sorry, we
Yep.
cannot perfectly screen magnetic field.
We can't perfectly screen them. We can try to screen them. Yeah. The idea is that we would have a source mass with it, which would be our ferroelectric crystal. We would polarize the nucleus spins. This distance here would be set by the mass of the axion, which tells you about the range of your force. And here you would have an NMR sample, so it would be polarized helium nuclei. Now, this is an NMR kind of experiment. So this source mass here, what we would do is we would put it on a linear stage. It would go back and forth like this. I still need to animate this slide. And it would do that back and forth motion at the frequency, which is the Larmor frequency of these spin samples here. And the result is like in an NMR, it will cause the effective magnetic field of the axion, and the source mass that's processing at this Larmor frequency will cause these helium spins to precess off their axis. And that precession of axis causes some magnetization that we can pick up with a squid. So this is similar to the Ariadne experiment. We've just changed the dimensions a bit, and we now have a different source mass, which is a ferroelectric crystal that's spin polarized. So here's a very preliminary plot of our reach. So this would be a crystal whose source mass was uranium. I'm just going to point out now that I know that's a bit contentious. We have yes, we have other projections that would, for example, use europium, which is also octapole deformed and less contentious. And in that case, your lines would be just below the QCD axion line. But I wanted to show you something against the advice of my advisor that actually hits the QCD axion line. And so basically these projection lines peak when you match the separation in your experiment to the range of the force that's set by the axion mass.
Sorry, and the coupling with the spin, you take 1 over FA or the mass?
1 over FAA.
And it has to be uranium-235.
No, it doesn't. So uranium-235 in principle would be great because it has this big shift moment and it's not so radioactive that, I mean, some of the issues of radioactivity would be that we need, in order to polarize the spins, this experiment needs to be cool. And if you have something radioactive, it will heat up your fridge. So that's no good. You would also harm your experimentalists. But uranium-235, uranium,
Minor problem.
yeah, minor problems. Uranium-235 has, it's not alpha decay, for example. I think it's gamma or beta. And it has a very long half-life. So actually, it would work if it wasn't for the fact that probably it would be hard to get people to give it to us. So you can probably work this out. 0.15 millimeters, and then the area is 300 times 0.15 millimeters squared. So yeah.
Proposal for Los Alamos. Yeah.
Okay.
Kilograms sitting around.
I think somebody should build it like this, so that's why I'm showing it to you.
This is not just pure uranium, right? You need this.
Yeah, it needs to be inside a material. Yeah.
What is the compound?
So if I go back to the materials table, it would be, well, actually, no, I would need to, I don't know the compound yet. I can definitely go back to the materials project and find you a crystal that has uranium and is ferroelectric. But I can't remember I don't know what the compound is yet.
Wait, 235 is the enriched one, 238 is the?
That's the one that people want.
Yeah, like, does this not work with 238?
No, no. I mean, it's okay. I can't remember if, no, it's even. So no, it wouldn't work.
Oh, yeah. Very important.
Yeah. So just a summary of these two experiments and the couplings they could look for. So in both of them, you're sensitive to the axions coupling to gluons. In this first setup, you could also use it to look for the axion coupling to electrons. I mean, here we discussed that we need two couplings. We also need this potentially model-dependent coupling of the axion to nucleons, but we took the QCD axion benchmark here. This experiment has sensitivity to masses between 10 to the minus 11 to 10 to the minus 7 electron volts, here 10 to the minus 5 to 10 to the minus 2. Here we said that the axion has to be the dark matter, whereas for this experiment, it doesn't need to be the dark matter. We're sourcing the axions off shell. And so for those who like their summaries in words, the QCD axion dark matter can excite vibrational modes in a piezoelectric crystal via its model-independent coupling to gluons. And now ferroelectric crystals can source QCD axion-mediated forces that we could detect using an NMR sample. And we believe that these would be complementary experiments to those performed with cavities. So thank you. Yes?
So does that mean people find axion using a different coupling, for example, axion photon coupling, analyzing the QCD axion band, and you can very quickly build an experiment because you know the mass. So you just build that crystal and
so I think I can't remember this. I can't remember exactly the numbers off the top of my head, but we tried, for example, using a photon coupling, and it's not as good in these setups as.
No, I mean if people use axion photon coupling.
Oh yeah, no.
Already find
Yes, no, you're right. So if you saw the QCD axion with an axion in this axion photon coupling, then yes, absolutely. If you were looking for the gluon coupling, that would tell you that it was the QCD axion.
What sets the 10 minus 5 would be for the ferroelectric one?
It's just basically the scale of the experiment you can build. So if I go back. You see, as you decrease the axion mass, your experiment gets bigger. At some point, you have to stop. So
that's just 1 millimeter.
yeah. So
Sorry, it's a 300.
yeah.
So what did you use for the input for the shift moment of uranium?
I think uranium was the order of a few times theta bar times E times femtometer. Is that the right dimensions?
The dimension should be distance cubed.
Yeah, femtometer cubed. Yeah.
But it's also the range of the force too.
Yeah, no, so yeah, so for example, this here, so yeah, you could potentially probe longer range of forces if you could build a bigger experiment, which we don't think you can do, so not easily anyway.
Short range fault, you need to probe smaller masses, you need much shorter
range. Yeah, I mean, your sensitivity goes down as well. As you can see, this line is better than this line. So if you make it smaller again, it's
closer and closer. Yeah, into shell.
Well, where does the 300 come from?
We asked Andy how big we can make it if we max this out. And he thought about it and said, I think about 300 times that distance. So
if you write your paper, you say, oh, the 300 paper is by consultation with this person.
No, he's actually going to write the section, so he will put his reasoning in there. This is still stuff we're working on, so.
For the summary of your first part, I'll go back to the first part. If I recall correctly, there's some properties you don't know how to calculate. You were just assuming them to be autoline. Do you foresee that it's actually not going to be autoline?
So this here is the quantity. It was this material dependent property that we thought would be order 1. In our paper, we have a dimensional analysis argument why we think it's order 1. And we did try to do this in DFT. And The thing is, we were actually getting the kind of numbers we expected, but our answer didn't have the right symmetry properties, so we decided we didn't trust it enough to put it in the paper. So it's possible. Yeah, so it's possible. Yeah, it's possible it won't be order one. We need to find out. Mhm.
So you said that, if you want to go below,
Mhm.
you have to make the laboratory bigger, right?
Mhm.
But, so am I correct? So if, you just have a matter, and then you just have a vector, then if the mass is kind of light, then you just pay the same force, right? Is it kind of coming?
Let me show you how the force scale. I think maybe I need to show you how the force scales again. Maybe that's where the confusion is. Oh God, sorry. Here.
You have two terms, right? I think
Yeah.
something like that.
This time, I mean, you have an exponential suppression as well.
No, but if you go to the right,
Mhm.
then it doesn't multiply. This is exponential.
Yeah, so it's a long-range force, no problem from that side. It's just they cannot source it. In fact, the source size is too small compared to the real life of the.
Yes, so I mean, what you can't see in here, for example, is that you.
Because you can just have the massive object here, and that can source the gravity.
But the gravitational field you source is proportional to how massive the object is. Okay.
So that is coming from GSGP.
Yeah, but their source do not have infinite mass. The density, the charge density.
Yeah, so here I mean, when you look at the overall effect, it will also have an enhancement factor that depends on the number of nuclei that are sourcing the axion in your sample, which is not here, for instance. This is just the effect for one diagram.
You can go below the long-range force is still there. Is the strength is small. I don't have the effective source.
So the force is not just this potential, that's what you're saying? Or?
The overall effect in your experiment, so the force is this, but the overall effect in your experiment will also have a factor that comes from the number of nuclei sourcing your effect.
But that is not related to the axion mass.
No.
Yeah, so going below,
so let's go just below, like a super below, that line. Then you can just forget about the first time in this bracket. You can also forget about this exponent, right?
Yeah, you can forget about all of that. It's just
This force just doesn't depend on axion mass.
yeah, you can ignore axion mass dependence, but on the per charge, you use the source. So this potential, what do you normalize this potential?
Or I thought that you have to just multiply the number of the source, like a number of the particles or number of the sources to this one, and that factor also doesn't depend on the axion mass.
I think the point might just be your best sensitivity was coming from the first term of data the second.
Yeah. Or maybe I thought maybe also it is related to the fact that we actually using the resonance. It's not just a static, you have this kind of shape, right?
And where does the M in this expression come? Like the M over R, why is there an X?
Why is there an M?
Oh, is it because of the derivative?
Yeah, derivative. I think you can just think of that just the income of Pascal source, and then the spin couples the derivative with. So then you can just take the derivative of the exponent, and that will give you. Okay, maybe you actually use the first time with this.
Then the question is why you're not sexted to the second.
I believe both of them are in that plot. So yeah, I'm a bit confused. I'm not sure what to tell you actually.
Maybe.
Yeah. Yeah, I can try to think about it for you more later, if that's okay.
For your first part, can you just explain to me the naive of the device without any manipulation? What's the fundamental frequency? What's the fundamental frequency and what's the best sensitivity to which particular axion frequency? What are those relations?
So
Let's say I have a, 4 centimeter
Yeah.
by 4 centimeter by 4 centimeter.
yeah, so you find the natural frequency. So the wavelengths, you find the natural frequency by just looking at the fundamental, like the zero mode that you would excite in the crystal, just when your wavelength matches the size of the crystal. The frequency of that mode should match the frequency of your axion, which is set by the mass of the axion.
So I want to match the mechanical frequency.
You want to match the mechanical frequency, yeah.
With my axiom.
Okay. Questions? Okay.
Thank you. Okay,